All right. Ooh, I shouldn't have that. All right. Good morning, everybody. Welcome back. So class recording has started. Yesterday, we spent a good amount of our time talking about the waves chapter and the different waves characteristics, and then different wave behaviors. The last question on the wave section, chapter 5, says a bright source of light is viewed through two polarizers whose preferred directions are initially parallel. Calculate the angle through which one sheet should be turned to reduce the transmitted intensity to half of its original value. Okay? So before we get into this, I wanted to review polarization because we have Brewster's law. So let's talk about polarization first. So, all right. So polarization. Here's the deal. When a light source produces light, not every light source, but a lot of light sources, they create light in all directions. Duh. But what we find is that when we look, light is basically a transverse wave. Not exactly, but for our intents and purposes, let's call it a transverse wave. And so that means it vibrates up and down as the wave is moving front to back, right? But what we find is that the requirement for something to be a transverse wave is that it's parallel to wave motion. So technically, if a wave is moving along, let's say, the x-axis, okay, any wave that vibrates in the z or y-axis is parallel, or sorry, perpendicular. Yes, because the z and the y-axis are both perpendicular to the x-axis. But any line in the YZ plane is also perpendicular to the x-axis. Yeah, does that make sense? Like when I phrase it that way? Okay. So that when we have all of these waves that are vibrating all perpendicular to the direction of wave propagation or the wave ray, that's what we call unpolarized light. But when we have all of them vibrating in the same direction, that's polarized light. So down here at the bottom of the screen, right, this is a representation of unpolarized light. If the wave ray is coming out of the board towards you. Does that make sense? If the waves are propagating from the board towards you, as they vibrate this way or this way or this way or this way, those are going to be unpolarized light. But in the one on the left over here, where all of the waves are vibrating in the same direction or the same plane, this would be polarized light. Does that make sense?
Polarization is when you're basically making the light a little more organized in terms of direction.
Yeah, I guess that would be a good way to describe it. Yeah. So, the one like sort of physical representation that we use is the idea of a picket fence. So if you have a picket fence, right, a fence that has openings that are vertical, it will only let waves that are vibrating in the vertical dimension go through. And that is what we refer to as a polarizer, a material that only allows waves with a certain orientation to pass through it. Yeah, real tiny, yes. And it's more like the molecular level, you know, like that it's only going to let certain things through. It also gets into like absorption versus transmission, like it's absorbing certain amounts of energy, but it's allowing other orientations of energy to pass through it.
And
so.
a polarizer is when it just kind of sorts it out through like small microscopic crevices.
Well, sorry, I should take that back. The polarizing filter, the size of it, is dependent upon the wavelengths of the waves that are traveling, right? A polarizer for light won't allow, like, let's say, radio waves to go through it, because those radio waves...
Sunglasses, right?
Sure.
And there's a bunch of different wavelengths of visible light.
Right, but they're all going at different orientations. But I would say, and I don't know this for sure, but I would say that the range of polarization, or the range of the polarizing filter, encompasses all of the visible light. Because visible light is only a very small portion of the electromagnetic spectrum. You know, like, yes, red light has a different wavelength than yellow, orange, green, blue, violet, right? But those wavelengths are so, the differences in the wavelengths are very small compared to the entire electromagnetic spectrum. So a polarizing filter that lets through one color of light is, generally speaking, going to let through all colors of light, because they're really not that different in wavelength. But, like, there is a big difference in visible light versus, like, radio waves. You know, they go much different.
These are like two different, it's like when you're looking at animals, if you're looking at a species of bird, you look at two parrots, they're more similar than like a parrot and a pelican.
Sure.
Awesome.
So up here where I just moved it right to the top right, it says a polarizer is any device that produces plain polarized light from an unpolarized beam. Fancy way of speaking, it only lets certain orientations of waves through, and it blocks the other ones.
So
Okay.
a Polaroid is basically, instead of letting them through, almost like through like those crevices or spaces.
It's basically like the second polarizer. It's like a Polaroid is a polarizer, but will no. Well, it depends on how they're oriented, right? If you have two polarizers that are oriented the same way, they'll both let through the same orientation of light. But if the second one is tilted, now it only lets through a portion of the light that was polarized.
And that's what sunglasses are in the Polaroids.
Yes.
Right? That's amazing.
Okay. So how much light gets through, or how much percentage of the wave intensity gets through, is brought to us by Malice's law. Right? When a plane polarized light is incident on an analyzer, its preferred direction will allow a component of the light to be transmitted. So again, even though we have plane polarized light, what we find is that a certain percentage will be allowed through because a certain component of that wave is allowed through. And the relationship is summarized down here in the bottom left. The intensity of the light is proportional to the amplitude, the transmitted energy, blah, 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 blah. And so what we end up with here is I is the intensity that is allowed through the polarizer. I naught, or I zero, is the original intensity. Cosine squared, or the theta in this equation, is the angle between the two polarizing filters, or how much they're tilted. So the amount of intensity that's let through, this I value, is dependent on how much intensity was incident on it and the angle between the two polarizing filters. Okay? Does that make sense?
Also, I have, this is really good, I just wanted to let you know, I have a weird thing with like Avon Lake scheduling that we had to talk about. This is Jerome was telling me, just after this.
Yeah,
That's
after
what I
this.
wanted to say. I should have said that first.
You probably should have, yes. Because we're in the group now. So.
Yeah.
Alright, so it says, a bright source of light is viewed through two polarizers whose preferred directions are initially parallel. So in this case, right, like we said, we have the two polarizing filters lined up so that they're letting the same orientation of waves through them. Does that make sense? Right. Calculate the angle through which one sheet should be turned to reduce the transmitted intensity to half of its original value. So if it's asking us to solve for the angle through which one sheet should be turned, right, we're solving for theta in that equation. Okay? Even though they didn't give us any numbers based on our description, we can make up our own numbers, right? So if we start here, okay, if we want the transmitted intensity to be half of the original value, there's a couple different ways we can do this, right? This is the original value, this is the transmitted frequency, right? So we can go 1 and 2, or we can go 0.5 and 1, whatever, right? We just need to make up some numbers. Good there?
Yes.
Okay? And then it's a little math, right? We're going to take the square root of both sides to get rid of that squared value, right? And then we need to solve for theta, so we're going to take the inverse cosine of both sides, right?
Wait, what's the 2? Or it says 1 equals 2 equals cosine in the second line. I was just a little confused. Oh, you just put in the ratio?
Alright. So
oh, so you just want to put a half in where the 1 is.
this is the original value.
Yeah.
This is the transmitted value. This is the original value. This is the transmitted value, right? So there's I mean, we can put any numbers in here that would represent the transmitted value being half of the original value.
That's easier.
2, 1. I could go 1 or 1/2 here. I could go 4 and 2. Whatever, right? We just have to reduce the intensity to half of its original value.
But this one's just easier to solve.
They're all easy to solve because you're going to end up with, regardless of what 2 numbers you put in here, you should end up with this equation on the next step.
Yeah.
Because you have to, if the original intensity is twice as much as the transmitted intensity, that should give you 1/2. And if I'm not mistaken, I believe theta should come out to be 45 degrees. Did you actually get that?
Yeah.
Okay. So, verification is always good. All right, good there? Okay. There were no questions in this section about any of, there's intensity, no, like refraction or refraction or reflection, all right? So, reflection's pretty easy, right? The only thing we really need to talk about with reflection is that angle of incidence equals angle of reflection, right? Whatever angle a ray enters the boundary, it's going to bounce out at that same angle, right? So, not, what?
That was the worst possible time to do that. He's just like, okay.
And then, like it says right here, that's our law of reflection. I equals R, or incident angle equals reflected angle. Usually, we measure those angles from a line that is perpendicular to the surface, or the normal line to the surface. But whether you measure them here, or whether you measure them with respect to the surface, the relationship still holds true, because you're going to get that same thing, right? So,
What was the thing a few pages back? Like partial polarization.
oh.
When it's reflected.
Oh, okay, sorry. That's Brewster's law. So what we find out is that a ray of light incident on the boundary between 2 media will, in general, be reflected and refracted. So when we get a wave that encounters a new medium, what we find out is that there is partial reflection and partial refraction. But the reflected ray, the one that bounces, comes out polarized. Okay? So, it says the reflected ray is always partially plane polarized. If the reflected ray and the refracted ray are at right angles to one another, then the reflected ray is totally plane polarized. So what we find is that reflection off of that boundary actually causes polarization, at least to a degree. Okay? In a specific orientation, it will come out totally polarized. Okay? So, like, yes. Yes, which is how polarized sunglasses actually work the best, okay? Polarized sunglasses work the best for driving and for being on the water, because the reflection comes off polarized. And so if you have the polarizing filter in your sunglasses to cut out a lot of that plain polarized light, it quote unquote reduces glare. It does happen at every medium, but remember, and we haven't talked about this yet, remember that in this case, for refraction, the index of refraction determines how much the ray bends when it goes into the new medium, right? If we set up the index of refraction in a way, or just by chance the index of refraction is set up where these two angles are perpendicular, the reflected angle, which we know is angle of incidence, angle of reflection, and the refracted angle, if these two are perpendicular to each other, the light that is reflected comes out totally polarized. It will be partially polarized regardless of what the reflected and the fraction. It will be partially polarized regardless of what this angle is right here between these two rays, but if they are perpendicular, it will be totally polarized, right? And so in a situation like water, we know the refractive index of water basically, right? I mean, depending on whether it's salt water or brackish water or fresh water, that can change a little bit, but they're minute differences. So we know what angle that ray is going to come in and then be refracted. We know then the angle of reflection is equal, so we can set up our polarizing filter like right here. Yeah, well, you don't want to catch all of it, right? Because if you catch all of it, you don't see anything, right? So that's why, you know, and this, right, this is not the only angle of incidence for the light rays. I mean, like, they're going to be coming in at all different angles. So you're not going to be totally polarized no matter where you are, just because of the way that those light rays are hitting the surface. But you can cut out a good portion of them, and that's, like I said, that's where we get into reducing glare, right? That reflected light off of the surface of the water, that's the one that's really tough, you know? So that's how polarizing sunglasses are really very effective. That's a situation where they're very effective. So, yeah.
Is that why a lot of people who love polarized sunglasses are like fishermen love them, because you can see the little swimming boys on the water?
Fishermen, boaters, I mean, like
Yeah,
the water.
so they can
Actually,
see fishes.
you know, I wear polarizing sunglasses. I wear polarized sunglasses when I drive, because,
Oh,
you know, so, I didn't used to, but now I'm getting old and, you know.
My mom does too. My mom and dad.
But I wear polarized sunglasses when I drive.
Yeah.
And the one time that I notice it especially is in the wintertime.
Yeah, 'cause
like when it's bright and sun, when it reflects
snow.
off that snow. So it's a big difference. So, yeah. But so it says Brewster's law relates the refractive index of medium 2 to the incident angle. Okay, and then we end up with that. So, and that's the refractive index that we would need in order to get this perpendicular arrangement that gets the reflected light to be totally plane polarized.
It's really fun to fish with those too, because it's like you can sometimes see the fish bite on your line and like get hooked.
So, I mean, that's just probably part of reducing the glare that's coming off of the water.
Yeah.
All right, good there. Does that make sense with that? And that actually is a pretty good lead-in to
Types.
These other two wave behaviors, right? Reflection and refraction, right? We just discussed, right, reflection and transmission, right? When an incident ray encounters a new medium, part of that ray is reflected and part of it is refracted or transmitted through the medium difference, but there is a change in the direction of that ray because of the different refractive index between the two of them, right? This right? Types of reflection. Depending on the smoothness of the surface, right, we can either get reflection that is basically all coming in and out at the same angle, or in something like this where we have diffuse reflection, we send light in, but because the surface is not completely smooth, it bounces off of the surface at an angle equal to the angle of incidence, but because the surface is not smooth, they all kind of come out at different angles, right? This is a question that comes up when we talk about, like, okay, so this is a white board. We tell you that white is a combination of all colors, right? This board or the periodic table on the wall are white because they reflect all the colors of light off of them. A mirror reflects all the colors of light off of it as well, but it's not white because a mirror is smooth, so all of the light comes in and all of it comes out in a nice orderly fashion, right? Does that make sense? But something that is white paper, the surface is imperfect, so that when the incident rays come in, depending on what portion of the surface they hit, they may go in all kinds of different crazy directions. So you're seeing all of that light, but it's all mixed together because it all ends up going in crazy directions. Whereas in a mirror, if this is a red ray of light, a red ray of light is coming out off of that. Does that make sense? How they're both reflection, and they both, white things and mirrors both reflect all colors of light, but white things, because their surfaces are not smooth, end up mixing all those colors together, whereas the mirror will basically bounce it right back out all orderly the way that it came in.
So mirrors are essentially just white things. Mirrors are white, but
White,
their surface
how about
is black.
how about white things are not smooth mirrors? So
White people are not smooth mirrors.
does that make sense? Yeah. All right. So that's reflection, right? And then it gets in, right? I mean, this is just, incident rays is the angle of incidence is equal to the angle of reflection. That's pretty much it for reflection. The angle that it comes in is the angle that it comes out. Like I said, usually we measure it from a line that is perpendicular to the reflecting surface, a normal line, but whether you say this angle versus this angle, or this angle versus this angle, you're going to get the same thing because those angles are always the same. Critical angle thing is next on refraction. Okay, so let's talk about refraction. All right. So, like we said, refraction is the bending of a light ray or a wave ray, because it doesn't just happen with light, it happens with everything. It's the bending of a ray due to the difference in medium, right? And that change of medium causes a change in speed, which causes the light ray to bend in a different direction, okay? Again, we measure these angles reference to the normal line, a line that's perpendicular to the surface or the boundary between the two mediums, right? Here, we have a less dense medium, we have a more dense medium. This is the first example. This is when you look at something in the water, right? Okay, does that make sense? Everybody okay with that? Okay. Here, I'll grab some pictures. So, in this case here, we have an incident ray. We, generally speaking, measure that ray with respect to the normal, okay? And then, so this is the incident ray, and then this is the angle of refraction as measured by the normal, okay? When we go from less dense to more dense, we actually get closer to the normal line. So if you measure this one versus this one, when we go from less dense to more dense, theta 1 is going to be greater than theta 2. I can get you guys pictures of this too, just like we talked about. This is a kind of a big section, and I didn't want to just print all of that. So. And then when we go from more dense to less dense, right? Here's theta 1, here's theta 2. Oh, no, that's not theta 2. This is theta 2. So in this case here, theta 1 is less than theta 2. This is why when we look at something in the pool, right, we see it at a specific spot, but it doesn't, like when you go, like if you're ever spear fishing, you know, 'cause I know probably you guys have a lot of experience spear fishing, right? You know, so, all the time. So, that when you see something in the water that's not actually where it is, because those rays bend as they go from the one medium to the other medium, and your eye doesn't necessarily understand that the ray bent, right? Okay. If we work in reverse here, right? Let's say, you know, there's your fish, right? Okay. Light bounces off of the fish. I'm going backwards here, so the light is coming this way as it approaches the boundary between the water and the air. But over here, right, when we go from a more dense medium to a less dense medium, we bend away from the normal. So theta 1, which would be this one here, theta 1, is less than theta 2, right? So it bends away, and this is like your eye. It's a terrible eye, but so your eye gets this wave, or gets this ray, but your eye doesn't really necessarily know that that ray bent when it reached the boundary. So if you trace back along this dotted line, your eye is telling you that the fish is actually there. Okay? No. This is what your eye sees, right? So, right? So, if you are spear fishing, don't aim at the fish. Aim in front. Aim closer to you.
How do you know it? Do you actually know how far?
Well,
Native Americans learn like it's
if
you
you can't just whip out your calculator right there, right? But you, I mean, but that does depend. But that does depend on, right, it depends on a couple of things. It depends on the angle of incidence and the angle of refraction, but it also depends on this value n, which we call the refractive index of that substance. Things going from water to air would bend differently than things going from glass to air. So, you know, when the light is coming in through that window, technically the things we see outside are not where they actually are, because there is some refraction that occurs as that light goes through the window. Right? But your eye, like I said, your eye doesn't necessarily know that. Right? So, let's see, where are we here? Right? So in this case here, you know, this is a pretty complex example, but right, with this ray traveling between two medium, right? There's one refraction. Like I said, this is the light that is coming in from outside, right? There's one refraction as the light goes from air to glass. There's a refraction there. Then there's one refraction as the light goes back out of the glass and into the air, or in this case, You know, they have water on the other side over here. This is why like you do the pencil in the glass of water trick, right? That the top of the pencil and the bottom of the pencil don't match up. It totally is.
It's a collision.
So, but those different refractions occur as we go from two different mediums, right? Here, as we go from less dense to more dense, the angle gets smaller, right? B is smaller than A, as measured to the normal line to that surface. And then we go from more dense to less dense, the angle actually gets bigger. So B here is actually bigger or smaller than C as it bends away from the normal line.
Sounds so cool.
So,
It essentially happens.
yeah, but this is also one of the things that we have to take into account when this affects how we observe things from Earth.
In space.
Well, we observe things in space, but the light from those objects, and the radio waves from that matter, because they refract as well, enter our atmosphere, and that causes a refraction. So we have to take that into account when we're looking at things, because they don't show up necessarily where we think they should show up, right? Does that make sense? It's also one of the problems that we initially had with the Hubble telescope, because say again. I think it was kind of more that we didn't. I don't know if we didn't account for, or maybe didn't account for correctly, the idea of that refraction. We always look at things from the surface of the Earth, and we have to contend with the atmosphere. Right, it wasn't focused properly because the waves aren't coming through that atmosphere, encountering that refraction that affects how we see things. So, same. That's a little different, but that gets into general relativity and the curvature of space-time and stuff like that. Yeah, the gravity lensing. Yeah, gravitational lensing. So, that kind of gets back to this, in that it's not refraction because it's not encountering a new medium as it travels through space. The curvature of space-time is actually causing those rays to come and bend, but it's similar to this situation of the spearfishing, because if this is, that's our eye, right? This is some big, huge spiral galaxy, right? Okay. And then this is some star way on the other side, right? The light from that star bends and comes here, but the light that left this side of the star bends and comes here.
That's is gravitational.
So no, you don't see 3 stars, you only see 2, because you can't see the original star because the big galaxy's in the way.
That's
right?
general relativity.
This is general relativity.
Yeah.
But then we see this.
It's an eye.
Right? And we see.
It's on the
Right?
scale.
So yeah, we see this star in 2 different places, or technically we could see it in 4 different places, because it's also happening out of the board and into the board, right? It does happen like that. So if we're at the right orientation, we would see a halo.
A Haley. I thought he was gonna say a
So-
Haley.
Does that make sense? We'd see a halo that that would be a complete circle, depending on if we're at the right orientation, the right distance, all that jazz. That. So, well, let's talk about critical angle.
Every time you want to draw an eye, just try to think you're teaching general relativity. I know, it's a pretty good eye.
Okay. So, we talked about that when a ray encounters a different medium, there will be partial reflection and partial refraction. Okay? But, here, let me get this picture. Okay. So yeah, the gravitational lensing is not refraction, but the idea of we see those rays coming from, or our eye interprets them where they came from, not necessarily where they're ultimately originated. Does that make sense?
Is black body radiation used?
Chapter 7. Yeah. That's not necessarily direction, that's more like the amount of stuff, right? So here, 3 things happen with the 3 different rays, right? So first, okay, for ray 1, we get partial reflection, partial refraction, okay? For ray 2, partial reflection, partial refraction. That angle is different because the angle of incidence is different, okay? But sorry, that one is meant to be something, right? Oh, we get that, that's good, okay. But there is an angle that we reach, an angle of incidence, where refraction will no longer occur, and we will get total reflection at that boundary, even though it might be a transmissible boundary of 2 media, right? So here, with this one, right, we end up with total reflection, okay? The angle that we talk about is called the critical angle. What angle of incidence results in total, or if we have an angle greater than that angle of incidence, total internal reflection, right?
Dependent on the indices?
It depends on, depending on indices of refraction. Keep in mind that we're always measuring that angle from the angle of incidence, or sorry, we measure the angle of incidence from the normal line. So here, this angle is getting smaller, right? But this angle is getting bigger, and that's the angle that we measure. We measure it from that normal line. So that angle is determined, where are we here? That angle is Snell's law. Where is Snell's law? Oh, there it is. Next one.
This is whiplash?
Oh my god, you're so late.
I did not. I believe I found. So.
Oh my god.
That's a really fun game.
Alright, so then here, to work out that critical angle, it does depend on the index of refraction. This is Snell's law right here, okay?
And
That determines the angle of refraction based on the index of refraction of the 2 materials. But in the case of critical angle, one of those angles is 90 degrees with reference to the normal line, right? So we get rid of that here and here, okay? Does that make sense?
yeah.
Really, or you can say no? Okay. So in this case, right, sine of 90 is 1. Do we understand why sine of 90? Okay, because I would, in this case here, okay, in these 2, in this case they have N2 on the bottom and N1 on the top, okay? So theta 1 is the angle of incidence and theta 2 is the angle of refraction. Does that make sense in this diagram? Okay. When we get the critical angle, this is what happens. The ray comes in to the surface, and at the critical angle, it travels along the boundary of the 2 surfaces. Okay? So theta 1 in this case, because this is the number 1, this is n1, right, is 90 degrees because we measure it with respect to the normal. Does that make sense? Okay. So then that means that theta 2 is the critical angle, okay? Here, yep, all right, okay. Sine of 90 is what? 1, right? So then, right, we can go n1 over n2 is equal to sine of theta 2, which just so happens to be the critical angle, okay? Does that make sense? In the case, this is for a specific, this would be the calculation for the critical angle, okay? We would solve for theta 2, and that would be the incident angle that we would need, okay? If, in the case of, like, let's say, vacuum, right, or whatever, if n1 is equal to, well, what do they have it here? Instead of hypothetically speaking, let's talk about it. Yeah, what do they have? I'm not sure why they just ditched n1 in this calculation right here. Not really sure. But yeah, we would need, depending on whatever the index of refraction is for those two substances, we could calculate the critical angle based on that ratio. Does that make sense? Get there? And the index of refraction is, I would imagine, is going to be given to you on the test. I mean, those are known values, unless they really wanted you to calculate it using Snell's law. And this is Snell's law up here. So
I think give me that one.
it should be in your, yeah, it'll be in your, yeah. How's that? Good there? That's pretty good as far as waves go. All right. So, yeah, there is one other section on diffraction, but quite honestly, I cannot remember seeing a sample problem that has dealt with diffraction on the test.
Are there AHL wave stuff?
No. Sorry. Some of the interference stuff and the interference patterns, but we went over that in class. Like when we did the waves, I did both the AHL and the core stuff. So we can obviously review it if we want to, but so. All right, how's that? Is that good for now? Diffraction. Yeah, it kind of like bends. So here, let's go.
How does it sound?
It happens to any wave. Like it does happen to light, but it happens so little with light that we don't really notice it all that much. So yeah, in this case here we have, right, this case where these are wave fronts approaching a barrier, and those wave fronts will bend around the barrier, and depending on the size of the wavelength, we can get a small amount of bending or a much tighter amount of bending depending on the wavelength of that material, or of the wave itself. So, okay. Does that make sense? Right, and it happens, so this is waves bending around a solid medium, right, it's just kind of like a barrier where we have waves on both sides of it, but it also happens, like, if we have the barrier here and here, it'll bend around the outside parts as well. This is why, like, if you're coming up to a corner in the hallway, you can hear what's going on around the corner, even though the waves aren't directly, you aren't directly in the path of those waves. Does that make sense?
Should report
Okay.
to the library at this time with their test ticket. They should pause their current test and report to the library.
And then we get
with
into
their test
two-source
ticket.
interference.
Thank you.
All right, how's that for waves?
Good.
Good. All right, we could probably actually, if we hustle, we could probably get chapter 6, circular motion and gravitation, actually done in our half an hour later today. So So it's a pretty short section. Like it's only 3 pages in the book, and then the so who Newton? Kepler, yeah, he's got 3 laws. So
He's only got trees.
yes, he has 3. So.